What unfolded on August 17th, 1943, high above Germany? And why did it reshape the fate of World War II in ways few understood at the time, as hundreds of B-17 flying fortresses thundered toward Schweinfurt's ball-bearing factories, the sky filled with fire, loss, and sacrifice? Bombers fell, airmen were lost, and the mission carried a brutal cost. Yet, far away in Canton, Ohio, an unseen advantage was already in motion, quietly rendering this deadly gamble far less decisive than anyone imagined. Stay with us, because what America had already built would change everything. The Schweinfurt raids. The lead bombardier peered through his Norden bomb sight as anti-aircraft flak erupted in black flowers around the formation. Below, through breaks in the industrial smoke hanging over central Bavaria, 5 factory complexes became visible. Schweinfurt. The name would become synonymous with catastrophic loss. Allied intelligence had identified these factories as Germany's Achilles heel. The German aviation industry alone consumed 2.4 million ball bearings monthly. Tank production, U-boat construction, truck manufacturing, all depended on these tiny precision components rolling between metal races. Destroy Schweinfurt's production capacity, military planners reasoned, and Germany's entire war machine might seize up like an engine without oil. The statistics seem to support the strategy. Kugelfischer Georg Schaefer, the largest complex north of the main rail yard, employed 11,700 workers even at war's end. Fichtel and Sachs operated southwest of the yard. 2 VKF factories, subsidiaries of Swedish SKF, occupied the city center and southern approaches. Together, these facilities produced approximately half of Germany's total ball-bearing output. The bombs fell. German Me-10-9s and FW-19s tore into the bomber formations. B-17 gunners claimed 288 enemy aircraft destroyed. The actual Luftwaffe losses numbered between 25 and 35 fighters. American losses were catastrophic and precise. Of 230 B-17s attacking Schweinfurt, 36 were destroyed, a 15.7% loss rate. Combined with simultaneous raids on Regensburg's Messerschmitt factories, 60 bombers went down that single day. The human cost was worse. Of 601 crewmen lost, 102 died. Another 381 became prisoners. The remainder evaded capture or were interned in neutral countries. Each B-17 carried 10 men. Each loss meant 10 families receiving telegrams. The bombing worked, temporarily. German ball-bearing production collapsed from 140 tons in July to 69 tons in August, then 50 tons in September. A 64% reduction. For exactly 8 weeks, the Allies seem to have found Germany's pressure point. Black Thursday arrived October 14th, 1943. The second Schweinfurt raid launched 229 B-17 bombers into German airspace. This time, 60 bombers failed to return, a 26% loss rate. Total casualties reached 594 missing, 40 wounded, 5 killed. Such losses were mathematically unsustainable. Crews calculated their odds. 35 missions constituted a tour. At 26% losses per mission, survival became a statistical impossibility. Deep penetration missions without long-range fighter escorts amounted to suicide runs. The raids stopped. P-51 Mustangs with drop tanks wouldn't arrive in sufficient numbers until early 1944. Yet, despite devastating raids, German ball bearing shortages never crippled war production. 3 factors prevented collapse. First, stockpiles. German factories had accumulated enormous reserves as buffers against disruption. Months of inventory sat in warehouses. Second, imports. Germany received ball bearings from neutral Sweden and Switzerland. Swedish SKF supplied approximately 10% of German requirements through 1943, increasing as domestic production cratered. Bearings were small, valuable, easily smuggled. British Bioac Mosquito aircraft flew dangerous missions to Sweden, returning loaded with ball bearings purchased by Allied agents. The British and Americans eventually pressured Sweden to reduce exports, even negotiating directly with SKF in April 1944, offering 88 million kroner to end German deliveries. But by then, Swedish bearings had sustained German production through critical periods. Third, substitution. German engineers redesigned equipment to use plain bearings, sleeve bearings, bushings, instead of ball bearings. These required more frequent maintenance and replacement, but could be manufactured with simpler technology and less critical materials. Post-war analysis confirmed what British Air Marshal Arthur Harris had argued from the beginning. The ball-bearing campaign, despite costing hundreds of American lives and dozens of bombers, achieved limited strategic effect. By 1945, Germany had assembled more bearing reserves than ever. Production had dispersed to underground facilities and smaller shops scattered across the Reich. While B-17s burned over Schweinfurt, American factories were solving the bearing problem differently. But what if the real victory wasn't won in the skies over Bavaria at all? What if it had been secured 45 years earlier in a St. Louis carriage shop? The friction problem and Henry Timken's origins. Friction transforms kinetic energy into heat while damaging surfaces and wasting energy. It represents a fundamental problem in all mechanical motion. Every wheel that turns, every axle that rotates, every machine that operates fights this invisible enemy. The man who could reduce friction fundamentally would achieve something of real value to the world. Henry Timken believed this absolutely. August 16, 1831. Tarmstead, Kingdom of Hanover. Henry Timken entered a world where transportation meant horses, wagons, and carriages. Prussia dominated German engineering. The Industrial Revolution was gathering momentum across Europe. Young Henry would see none of it firsthand for long. At age 7, Timken immigrated to the United States with his family. They settled in Missouri, a frontier state where practical skills mattered more than formal education. The boy, who might have become a German engineer, became an American craftsman instead. As a teenager, Timken apprenticed to a leading carriage and wagon maker. He learned wood selection, joint construction, wheel building, spring mounting. He discovered how carriages failed, axles wore, wheels wobbled, bearings seized. The friction problem revealed itself in broken vehicles and dissatisfied customers. By age 24, Timken had established his own carriage factory in St. Louis. He built reputation on quality and innovation. Customers wanted vehicles that lasted. Timken wanted to give them something better than what everyone else offered. In 1877, Timken received a patent for the Timken buggy spring. The innovation sounds trivial now, a spring design for carriages. But the spring's performance made it widely adopted throughout America. Numerous companies produced it on a royalty basis. The patent made Timken well known nationally. His carriage business flourished. The spring's success provided financial security. More importantly, it demonstrated that small mechanical improvements could create substantial competitive advantages. Timken had learned a crucial lesson: solve a real problem better than anyone else, and the market responds. Around 1895, Timken took interest in problems created by friction in wagon design. He was 64 years old. Most men that age were contemplating retirement. Timken was contemplating revolution. Conventional bearings of the 19th century worked adequately for reducing friction under vertical loads. A wagon sitting still, or rolling straight forward on level ground, presented simple engineering challenges. Existing bearing designs handled these conditions acceptably. Problems emerged when wheels had to bear heavy loads from the sides. Vehicles turning corners generated forces perpendicular to the axle. Wheels hitting ruts or rocks experienced sudden thrust loads parallel to the axle. Combined loading conditions, radial and thrust loads simultaneously, destroyed conventional bearings rapidly. Ball bearings represented the most common anti-friction bearing of the era. Their design was elegant. Spherical balls rolled between an inner and outer race, reducing friction through rolling contact instead of sliding contact. They worked excellently for light loads and high speeds. Machine tools, bicycles, light machinery, ball bearings excelled in these applications. But ball bearings had limitations. When subjected to heavy radial loads and thrust loads simultaneously, exactly what wagon wheels experienced when turning while carrying weight, ball bearings wore quickly. The contact point between ball and race was geometrically tiny. All load concentrated at these points. Stress levels became enormous. Metal deformed. Bearings failed. Timken studied the problem with help from his two sons and a nephew. They weren't trained engineers in the European sense. They were practical men who built things, tested them, and observed what worked. The family began experiments to make a better bearing. The solution they developed would change everything. So, what radical design could possibly outperform a technology that Germany's finest engineers had spent decades perfecting? Inventing the tapered roller bearing, the concept was revolutionary precisely because it abandoned spheres entirely. Instead of balls, use tapered rollers. Instead of flat races, use cone-shaped races. Instead of simple circular geometry, embrace angular complexity. The rollers would be cone-shaped, arranged at an angle between cone-shaped races. This geometry would allow the bearing to handle both radial loads, perpendicular to the shaft, and thrust loads, forces parallel to the shaft, simultaneously. Exactly what vehicle wheels needed, exactly what ball bearings couldn't provide efficiently. May 1st, 1898. Henry Timken received 2 patents for his tapered roller bearing design. The innovation was profound in ways that wouldn't become fully apparent for decades. The physics were elegant. A ball bearing contacts its race at a point. Under load, this point deforms into a small ellipse, but contact area remains tiny. Stress concentrates intensely at these microscopic contact zones. Increase the load, and the stress increases proportionally. Eventually, the metal yields, the bearing fails. A tapered roller contacts its race along a line. Under load, this line deforms into a narrow rectangle. Contact area is much larger. Stress distributes over greater surface area, reducing peak stress at any single point. The same load that would destroy a ball bearing becomes manageable for a tapered roller bearing. Load distribution followed different principles. In ball bearings under combined loads, only a few balls carried most of the load. The geometry meant that balls, in certain positions, bore disproportionate stress, while others contributed minimally. In tapered roller bearings, all rollers shared loads more evenly due to the cone geometry and precise positioning. The design offered another advantage ball bearings couldn't match: adjustability. Tapered roller bearings could be preloaded, adjusted to eliminate clearance and optimize contact. Mechanics could compensate for wear by tightening the bearing. Ball bearings had fixed clearances determined during manufacturing. Once worn, they required replacement. Heat dissipation mattered for continuous operation. The larger contact area in roller bearings conducted heat away more effectively, reducing operating temperatures. Cooler bearings lasted longer. They maintained tighter tolerances. They performed more predictably. Timken's bearing could handle 5 times the load of an equivalent ball bearing while maintaining lower friction and longer life. 5 times. The improvement wasn't marginal. It was transformative. In 1899, Timken incorporated the Timken Roller Bearing Axle Company in a corner of his St. Louis carriage factory. The name told the story: roller bearings for axles. The application was specific. The company grew so quickly that in 1901, Timken made a strategic decision. He relocated to Canton, Ohio. The reasoning was sound. The emerging automotive industry centered in Detroit and Cleveland. Steelmaking concentrated in Pittsburgh and Cleveland. Canton sat within easy reach of both. Proximity to customers and suppliers would matter. The move positioned Timken perfectly for the automotive revolution. Henry Ford introduced the Model T in 1908. Automobile production exploded. Every car needed bearings, wheels, transmissions, differentials, steering assemblies. Timken bearings could handle automotive loads better than ball bearings. The market was enormous and growing exponentially. But while Timken developed roller bearings in America, across the Atlantic, Germany was building a different kind of dominance. A dominance based on balls, not rollers. A dominance built on precision manufacturing and global distribution. A dominance that would become a strategic weapon. The question wasn't whether Timken's design was superior for heavy loads. The physics proved that conclusively. The question was whether an American company with a superior design could compete against German manufacturers with established markets, advanced metallurgy, and decades of experience. How had Germany come to dominate global bearing production so completely that America would enter World War I dependent on enemy technology? German dominance versus American innovation. In 1883, German entrepreneur Friedrich Fischer and his son pioneered mass production of precision steel balls in Schweinfurt using a grinding machine. The invention seems simple in retrospect. A machine that could grind steel balls to precise spherical tolerances, consistently, repeatedly, economically. But precision ball production had eluded manufacturers for decades. Fischer's factory merged with Georg Schaefer's shop to become Kugelfischer Georg Schaefer in 1909. The company name would appear in Allied bombing reports 54 years later. But in 1909, it represented the cutting edge of precision manufacturing. Another company moved even faster. Svenska Kullergerfabriken, Swedish ball bearing factory, founded in 1907 under the SKF abbreviation. The company's founder understood that bearing production was necessary, but distribution created wealth. SKF rapidly expanded globally with aggressive strategy. By 1908, SKF operated branch offices in Germany and France. By 1909, subsidiaries existed in New York, Britain, Denmark, Norway, Belgium, Holland, and Russia. This wasn't gradual expansion. This was blitzkrieg capitalism. Within 2 years of founding, SKF had established itself across 3 continents. SKF became the world's largest bearing manufacturer through relentless expansion and strategic positioning. They understood markets. They understood distribution. They understood that controlling supply chains created competitive moats. Before World War I, most ball bearings used in America were imported from Germany. American manufacturers purchased German bearings because German bearings were superior. German companies had established dominant positions through superior metallurgy, precision manufacturing, and an aggressive global expansion. German metallurgists understood steel composition at atomic levels. Carbon content, grain structure, heat treatment protocols, these weren't mysteries to German engineers. They were sciences. German bearing steel outperformed American bearing steel because Germans had invested decades in materials research. Precision manufacturing favored German firms. Tolerances measured in microns. Surface finishes measured in micro-inches. German machine tools cut more accurately. German measurement systems verified more precisely. German quality control rejected more ruthlessly. Henry Timken's travels to Germany in 1892 and 1895 provided competitive intelligence that proved valuable. He observed Daimler and Benz's internal combustion engine technology. He witnessed advanced bearing development. He understood viscerally that Europe was years ahead of America in bearing production. But Timken saw something German engineers missed. He recognized that ball bearings, despite German excellence in manufacturing them, had fundamental limitations for heavy load applications. Geometry constrained performance. No amount of precision manufacturing could overcome point contact physics. Timken's tapered roller design offered advantages that German ball bearings couldn't match, regardless of manufacturing quality. For heavy load applications, trucks, railroad cars, industrial machinery, tapered rollers vastly outperformed ball bearings. The geometry distributed loads across a line of contact rather than a point, dramatically increasing load capacity. When World War I began in August 1914, Germany's ball bearing monopoly became a strategic weapon. The British blockade cut German exports immediately. American industry, dependent on German bearings, faced shortages. Prices spiked. Delivery times extended. Production schedules slipped. American manufacturers found themselves unable to quickly substitute ball bearings because precision ball production required specialized machinery and expertise concentrated in Germany. You couldn't just decide to manufacture precision ball bearings. You needed grinding machines, measuring equipment, metallurgical knowledge, trained workers. The infrastructure didn't exist in America. The Timken Company, however, already had production capacity for tapered rollers. A different technology, a different manufacturing process, a technology that worked better for many applications anyway. World War I demonstrated that tapered roller bearings could replace ball bearings in most military vehicles. Timken bearings equipped trucks, artillery carriages, and heavy equipment. Performance proved excellent. Reliability exceeded expectations. Military procurement officers took notice. The war exposed German bearing dominance as both an economic advantage and a strategic vulnerability. America learned a hard lesson about supply chain dependencies. Would one man's vision and one company's production capacity be enough when the world needed bearings by the millions? Building the Timken Empire, 1920 to 1940. By 1920, the Timken Company was making 90% of America's tapered roller bearings. The statistic represented near total market dominance in a specific technology. Timken didn't compete with German ball bearing manufacturers on their terms. Timken had created a separate category and owned it completely. The company operated bearing plants in Columbus, Ohio, opened in 1920, and Canada in 1922. These facilities would eventually expand globally, but the initial focus remained North America, where demand was exploding. Railroad adoption proved crucial for establishing credibility. In 1923, Timken bearings were tested on streetcars running between Canton and Cleveland. The route provided perfect testing conditions, frequent stops, heavy loads, constant operation. The bearings performed flawlessly. Testing expanded to Wheeling and Lake Erie Railroad boxcars. Freight cars represented brutal applications, heavy loads, shock impacts, minimal maintenance, contaminated environments. Boxcars sat in rail yards for weeks, accumulating dirt and moisture, then hauled 60-ton loads across rough track. Bearings either survived or failed spectacularly. Timken bearings survived. By 1926, the Chicago, Milwaukee, St. Paul, and Pacific Railroad ordered Timken bearings for high-speed trains. The Burlington Zephyr and Santa Fe Super Chief represented the pinnacle of American passenger rail. These weren't freight applications. These were showcase trains where reliability mattered absolutely. Railroad companies bet their reputations on Timken bearings. But Henry Timken never saw this success. He died March 16, 1909, in San Diego, California, before his invention's full impact became apparent. He was 77 years old. His sons, H. Timken and W.R. Timken, continued building the company according to principles their father established. In 1917, facing World War I steel shortages, Timken made a decision that would prove critical for decades. The company began steel and tube-making operations in Canton to vertically integrate and control bearing steel quality. The decision seemed expensive and risky. Steel production required blast furnaces, rolling mills, enormous capital investment. Most bearing manufacturers purchased steel from suppliers. Why manufacture steel when steel companies existed? Because making your own steel meant controlling composition, heat treatment, and quality at every step. Bearing steel requires precise carbon content, uniform grain structure, and freedom from inclusions. Microscopic imperfections cause bearing failures. Inconsistent metallurgy produces inconsistent bearings. By producing steel internally, Timken ensured bearing quality while protecting against supply disruptions. Wars disrupted steel supplies. Economic downturns affected steel availability. Vertical integration provided security. The company entered the Great Depression in strong financial position. Its performance placed it among the most solid, well-managed industrial firms of the 1930s. While competitors struggled, Timken diversified, expanding into non-automotive markets, agriculture, machine tooling, industrial equipment, and rail softened depression impacts. Farmers still needed tractors. Factories still needed machinery. Railroads still hauled freight. Diversification provided stability. During the early 1930s, Timken developed bearings for propeller drive shafts, expanding into shipbuilding. U.S. Navy contracts followed. Naval applications demanded reliability. Ships operated far from repair facilities. Bearing failures at sea created dangerous situations. The Navy needed bearings that worked. In 1932, Timken began manufacturing removable rock bits for construction and mining equipment. The product line seemed unrelated to bearings, but rock bits provided outlets for steel production during depressed markets. Vertical integration meant Timken could manufacture various steel products when bearing demand slumped. When H. Timken died in 1940, his son, H. Timken Jr., became chairman. The company operated manufacturing facilities in Canton, Columbus, Mount Vernon in Ohio, plus Canada, Britain, France, and South Africa. Timken employed thousands and produced bearings for virtually every industry. The company had evolved from a corner of a St. Louis carriage factory to a global industrial enterprise. Production capacity existed. Distribution networks functioned. Product quality was established. Management succession had occurred smoothly. Then war came to Europe again. This time, America would enter the conflict with bearing production capacity that Germany couldn't bomb, couldn't blockade, and couldn't match. Could factories in Ohio really outproduce the entire German industrial machine when the world's largest mechanized war demanded bearings by the hundreds of millions? The bearing war within World War II. By 1943, Allied intelligence identified ball bearings as a critical German vulnerability. Albert Speer, German armaments minister, stated, as early as September 20th, 1942, I had warned Hitler that the tank production at Friedrichshafen and the ball bearing facilities in Schweinfurt were crucial to our whole effort. Speer understood industrial warfare. Modern mechanized combat consumed bearings voraciously. Every tank used dozens. Every aircraft required hundreds. Every truck needed scores. Multiply by hundreds of thousands of vehicles, and bearing requirements became astronomical. When World War II began, Timken's production increased dramatically. The company opened several new Ohio facilities to meet military demand. Timken Ordnance Company in Canton, established 1941, built approximately 80,000 gun tubes over the next 2 years. The Zanesville bearing plant opened in 1943. Other locations included Columbus and Newton Falls. During the war, Timken's output more than doubled its previous peak. The statistics tell the story with brutal clarity. Every U.S. Jeep used 24 Timken bearings. With 660,000 Jeeps delivered to the military, Timken produced over 15.8 million bearings for Jeeps alone. Just Jeeps. Just one vehicle type. Trucks required dozens more bearings each. The standard 2.5 truck needed bearings in wheels, transmission, differential, transfer case, drive shaft. Multiply by hundreds of thousands of trucks, and the numbers become staggering. Tanks used Timken bearings in tracks, wheels, turrets, and transmissions. Sherman tanks, Grant tanks, Stuart light tanks, every American armored vehicle rolled on Timken bearings. Artillery pieces used them in traversing mechanisms and recoil systems. Aircraft landing gear depended on them. ship propeller shafts required massive custom bearings. The advantage wasn't just that Timken bearings worked. They often worked better than ball bearings for military applications. Load capacity mattered most. Tapered rollers handled combined radial and thrust loads far better than ball bearings. Tank tracks and truck wheels experienced exactly these combined loads constantly. A tank track roller supports vertical load from the vehicle's weight while simultaneously experiencing lateral loads from steering and thrust loads from acceleration. Ball bearings struggle with combined loading. Tapered rollers excel at it. Durability became critical in combat conditions. Line contact between roller and race versus point contact in ball bearings distributed loads, reducing stress and extending life. Military vehicles operated under conditions that destroyed civilian equipment. Overloading, shock impacts, poor maintenance, contaminated lubrication, extreme temperatures, combat created the worst possible bearing environments. Maintenance considerations favored tapered rollers. Tapered roller bearings could be adjusted to compensate for wear. Field mechanics could tighten bearings as they wore, extending service life. Ball bearings, once worn, had to be replaced. In combat zones, replacement meant downtime. Downtime meant vulnerability. Manufacturing advantages proved decisive. Timken controlled its entire supply chain from steel production through bearing assembly. No dependence on imports. No reliance on external suppliers. No vulnerability to submarine warfare or blockades. German engineers knew tapered rollers existed. The technology wasn't secret, but German bearing manufacturing was concentrated in ball bearings. Converting production would require retooling entire factories, retraining thousands of workers, and redesigning millions of pieces of equipment. Impossible during wartime when every factory operated at maximum capacity producing existing designs. By war's end, Timken had produced hundreds of millions of bearings for Allied military equipment. The company's vertically integrated model, making steel, machining bearings, and controlling quality end-to-end, proved superior to relying on global supply chains that wars disrupted. Albert Speer later admitted that if the Allies had concentrated on bombing ball bearings, 2 months later, it will weaken war production fundamentally, and 4 months later, the war production will stop completely. But the admission was theoretical. Germany had stockpiles, imports from Sweden, and substitution options. Meanwhile, American factories faced no such vulnerabilities. Production ran continuously. Quality remained consistent. Supply never faltered. German armaments minister Albert Speer spent the war worried about ball bearing supplies. His American counterpart didn't have that concern. Timken had it covered. The bearing war was won not in the skies over Bavaria, but in factories in Canton, Ohio. So why does a story about bearings, perhaps the most unglamorous component in any machine, still matter 8 decades after the war ended? Post-war legacy to present day. Following World War II, much machinery shipped to Europe under the Marshall Plan was equipped with Timken bearings. American economic assistance rebuilt European infrastructure. American bearings helped the machinery function. The company established broader presence in markets where European competitors had previously dominated. The antitrust case that haunted the company came to a head post-war. United States versus Timken Roller Bearing Company alleged Timken conspired with British Timken Limited and French Timken to restrain trade through territorial restrictions. during the war. These restrictions created problems. Australia, in British Timken's territory, desperately needed bearings for war production. British Timken couldn't supply adequate quantities. They were overwhelmed meeting UK military needs. Australian distributors clamored for American Timken bearings, but territorial agreements prevented direct supply. December 4th, 1940. Correspondence between Timken executives showed the dilemma. We were advised by the British Purchasing Commission that they will very likely take over all purchases of anti-friction bearings for Australia. Internal memos documented how territorial agreements interfered with wartime production. After several appeals, the Supreme Court ruled in 1951 that Timken had conspired with foreign affiliates in restraint of trade. The decision forced restructuring of international operations, but didn't slow Timken's growth. By 1960, Timken operated in the United States, Canada, Great Britain, France, South Africa, Australia, and Brazil. In 1974, Timken opened sales operations in Japan, bringing American tapered roller bearings to compete in the world's most demanding bearing market. Japanese manufacturers were legendary for quality standards and precision manufacturing. Timken competed successfully. Throughout the 1970s and 1980s, Timken expanded into Italy, Korea, Singapore, and Venezuela. The global footprint grew systematically. In 2003, Timken acquired competitor Torrington Company for $840 million, doubling company size and creating the world's third largest bearing manufacturer. In 2014, the company separated bearing and steel operations. Timken Company continued manufacturing bearings, while Timken Steel, now Metallus, became independent. The vertical integration strategy that began in 1917 ended nearly a century later. As of 2024, Timken Company posted $4.6 billion in sales and employs more than 19,000 people globally, operating from 45 countries. The company remains the world's largest manufacturer of tapered roller bearings, a position held continuously since the 1920s. The product line has expanded dramatically. Timken now manufactures ball bearings, spherical bearings, cylindrical bearings, thrust bearings, plain bearings, housed units, and precision bearings. The company produces gear drives, automated lubrication systems, belts, chain, couplings, linear motion products, and power transmission services. But tapered roller bearings remain central. From bearings the size used in disk drives to 9-ton custom bearings made for heavy forges, Timken dominates the market with approximately 30% global market share in tapered rollers. Modern bearing technology vindicated Henry Timken's 1898 innovation. Today's heavy equipment overwhelmingly uses tapered roller bearings, automotive wheel bearings in trucks, SUVs, and heavy-duty vehicles, aerospace landing gear and gearbox applications, rail freight car axles and locomotive drives, industrial wind turbines, mining equipment, steel mills, construction excavators, cranes, heavy machinery. Ball bearings are best for high-speed, light-load uses, while tapered roller bearings dominate heavy-duty applications with compound loads. The core physics Henry Timken developed in 1898 still apply today. Line contact spreads loads more effectively. Tapered shapes handle both radial and axial forces, and adjustability allows better performance under changing conditions. These simple principles became the foundation of a global industry. The ultimate irony remains. Henry Timken was German. Born in Hanover, he emigrated at age 7 and became thoroughly American. His engineering sensibility reflected German thoroughness and precision, but he saw what established German manufacturers. Were you surprised to learn how a quiet mechanical innovation kept America moving in 1940? And how Timken's tapered rollers changed the course of wartime logistics? Share with us which detail about bearings and battlefield mobility shocked you the most.